So here's something worth thinking about as you settle in tonight. Right now, wherever you are, whatever device you used to start this playing, that device is built on a principle that Albert Einstein, arguably the most brilliant physicist who ever lived, called spooky. Not spooky in a Halloween way, spooky in a way that genuinely unsettled him, that he spent the last 3 decades of his life trying to disprove, and that he ultimately went to his grave in 1955 still refusing to fully accept. And the thing is, he was wrong. The spooky thing turned out to be real. And understanding it, even just a little, even just enough to let it wash over you as you drift off tonight, that's one of the most quietly mind-bending journeys you can take. We're going to talk about quantum entanglement. And I know, that phrase alone can feel like a wall. It sounds like something from a physics textbook you'd never voluntarily open, or from a science fiction movie where someone waves their hands and says something about quantum to explain why the plot doesn't make sense. But here's the thing. Entanglement is real. It's been experimentally confirmed thousands of times. It's the basis of technologies being built right now. Quantum computers, quantum encryption, sensors that can detect gravitational waves. And at its heart, the idea is actually not that complicated. It's just deeply, deeply weird. And the weirdness is the fun part. So let's start at the very beginning. Not with entanglement itself, we'll get there, but with the world that made entanglement possible. Because entanglement doesn't make any sense unless you first understand, at least a little bit, why the physics of the very small turned out to be so shockingly different from the physics of everything you can see and touch. Picture the year 1900, the turn of the century. Physics as a field is feeling pretty good about itself. There's this famous, possibly apocryphal story that Lord Kelvin, one of the most respected physicists in Britain, supposedly said something to the effect of, "There is nothing new to be discovered in physics now. All that remains is more and more precise measurement." Whether he actually said that exact thing is debated, but the sentiment was real. Newtonian mechanics could predict the motion of planets. Maxwell's equations described electricity and magnetism beautifully. Thermodynamics was well understood. The universe seemed, fundamentally, like a giant clockwork machine. You set the initial conditions, you knew the laws, and in principle, you could predict everything that would ever happen. Deterministic, clean, elegant. And then, in December of 1900, a German physicist named Max Planck accidentally kicked over the first domino that would eventually demolish that entire picture. Planck wasn't trying to start a revolution. He was trying to solve a very specific, very annoying problem called the ultraviolet catastrophe. Here's what that was about. When you heat up an object, say, a piece of metal, it glows. First, it glows red, then orange, then white, then bluish-white as it gets hotter. Physicists wanted to predict exactly how much light energy an object would emit at each color, at each frequency. And when they used the classical physics of the time to calculate this, the math worked fine for low frequencies, for red light, for infrared. But as you moved toward higher frequencies, toward ultraviolet light and beyond, the equations predicted that the object should emit infinite energy. Infinite. Which is obviously absurd. A hot piece of metal does not destroy the universe. This was the catastrophe. The math was blowing up, and nobody could figure out why. Planck's solution was strange, and even he didn't fully appreciate how strange it was. He proposed that energy wasn't emitted continuously, like water flowing from a hose, but in tiny, discrete packets, little chunks. He called them quanta, from the Latin word for how much. Each quantum of energy was proportional to the frequency of the light, linked by a tiny constant that we now call Planck's constant. And when he plugged this assumption into the math, the ultraviolet catastrophe vanished. The equations behaved. The predictions matched what people actually measured in laboratories. Now, Planck himself thought this was probably just a mathematical trick, a clever workaround. He didn't necessarily believe that energy really came in little packets. He thought maybe it was just a useful way to make the equations work, and eventually someone would figure out the deeper, continuous explanation. He was a conservative man by temperament, deeply rooted in classical physics. He'd basically lit the fuse on a revolution, and then spent years hoping the bomb wouldn't actually go off. But it did, because 5 years later, in 1905, a 26-year-old patent clerk in Bern, Switzerland, took Planck's idea and ran with it in a direction nobody expected. That patent clerk was Albert Einstein, and 1905 was his miracle year, the year he published 4 papers that each would have been enough on its own to make a career. One of them was about special relativity. Another was about Brownian motion, providing evidence that atoms actually exist. But the one that's relevant to us tonight was about the photoelectric effect. Here's the setup. When you shine light on certain metals, electrons get knocked loose from the surface. That's the photoelectric effect. Classical physics said that brighter light, more intense light, should knock the electrons out with more energy. But that's not what happened. What actually happened was that the energy of the ejected electrons depended on the color of the light, its frequency, not its brightness. You could shine a very dim blue light on the metal and get energetic electrons. You could blast it with an incredibly bright red light and get nothing at all. Below a certain frequency threshold, no electrons came out, no matter how bright the light was. Einstein's explanation was radical. He said light itself comes in quanta, in little packets of energy, which we now call photons. Each photon carries an amount of energy determined by its frequency. A blue photon carries more energy than a red photon. When a photon hits an electron in the metal, it's an all-or-nothing transaction. If the photon has enough energy, the electron gets knocked free. If it doesn't, nothing happens, no matter how many low-energy photons you throw at it. It's like trying to knock down a door. You can throw 1,000 ping-pong balls at it and nothing happens. But one well-thrown bowling ball does the job. The energy per particle matters, not just the total amount. This was the moment when quanta stopped being a mathematical trick and started being something real. Light, which everyone had been quite sure was a wave. Maxwell had proved it was a wave, for goodness sake, and interference experiments going back to Thomas Young in 1801 had demonstrated it beautifully. Light was also, somehow, a particle. Not one or the other, both, depending on how you looked at it. And this, right here, is where the strangeness starts to seep in. Because we're not talking about a minor adjustment to the classical picture. We're talking about a fundamental shift in what reality means at the smallest scales. Things down there don't behave like tiny billiard balls. They don't behave like tiny waves either. They behave like something that has no analogy in your everyday experience, something that can be both and neither, depending on what question you ask. Think about that for a second. The physics that governs everything you can see, a ball flying through the air, a planet orbiting a star, water flowing downhill, that physics is deterministic. You know where things are, you know how fast they're going, and you can predict what happens next. But down at the atomic scale, the rules are fundamentally different. And the people who discovered this didn't accept it easily. It took decades of argument, experiment, heartbreak, and some genuinely bitter personal feuds before the new picture came into focus. Let me tell you about one of those people, because his story matters a lot for where we're headed. Niels Bohr, Danish physicist. Born in Copenhagen in 1885, his father was a physiology professor, his mother came from a wealthy banking family, and young Niels was, by all accounts, a deeply thoughtful kid. Not flashy, not a prodigy in the way Einstein was, but persistent and philosophical. He had a habit of thinking about problems for a very, very long time before saying anything, and when he finally spoke, people listened. In 1913, Bohr proposed a model of the atom that was, frankly, a beautiful mess. He took the new quantum ideas and applied them to the structure of the atom itself. The picture at the time, thanks to Ernest Rutherford's experiments, was that an atom had a tiny, dense nucleus with electrons orbiting around it, like planets around a sun. But there was a problem with this picture. Classical physics predicted that an orbiting electron should continuously radiate energy. It's an accelerating charged particle, after all, and spiral inward, crashing into the nucleus in a fraction of a second. Every atom in the universe should collapse almost instantly. And yet, here we are. Atoms are stable. You're made of them. They're clearly not collapsing. Bohr's solution was to simply declare, and I mean declare, because he couldn't fully derive it from first principles, that electrons can only orbit at certain specific distances from the nucleus, certain allowed orbits, quantized orbits. An electron in one of these orbits doesn't radiate energy. It just sits there, stable. And when an electron jumps from a higher orbit to a lower one, it emits a photon with exactly the right energy to account for the difference. Not a continuous glow, but a specific, discrete flash of a specific color. And when you look at the light emitted by hydrogen atoms through a prism, you see exactly that. Not a continuous rainbow, but a series of sharp, distinct colored lines. Bohr's model predicted the exact wavelengths of those lines. It was stunning. But it was also, let's be honest, kind of held together with tape and hope. Bohr couldn't explain why those particular orbits were allowed. He just said they were. The model worked beautifully for hydrogen with its single electron, but got increasingly messy for heavier atoms with more electrons. It was a transitional theory, 1 foot in the classical world, 1 foot in the quantum world, not fully comfortable in either. And this is important because it set the stage for what happened next. Through the 1920s, a new generation of physicists, many of them astonishingly young, would build the full mathematical framework of quantum mechanics. Werner Heisenberg, who was 23 when he formulated matrix mechanics in 1925 on the island of Helgoland, trying to escape his hay fever. Erwin Schrödinger, a bit older and more established, who in 1926 developed wave mechanics and his famous equation while on a romantic holiday in the Swiss Alps. And yes, historians have spent considerable effort trying to figure out who he was there with, because it apparently wasn't his wife. Paul Dirac, the quiet, almost eerily precise Englishman who unified their approaches and predicted the existence of antimatter. Max Born, who figured out what Schrödinger's wave function actually meant, that it described probabilities, not certainties. These people, most of them in their 20s, were building a new theory of reality from scratch, and they argued about it constantly. Not just about the math was coming together, and it worked spectacularly well, but about what it meant. What does it mean to say that an electron doesn't have a definite position until you measure it? What does it mean to say that the act of observation changes the outcome? what does probability even mean when you're talking about a single particle? And here's where the two camps start to form. Because on one side, you had Bohr, along with Heisenberg and Born and most of the younger generation, developing what would become known as the Copenhagen interpretation. The idea, roughly, is that quantum mechanics is complete. The probabilities aren't just reflecting our ignorance, they're fundamental. An electron genuinely doesn't have a definite position until you measure it. The wave function isn't describing something hidden underneath. It's describing all there is to describe. Reality, at the quantum level, is inherently probabilistic. And on the other side, increasingly alone, increasingly frustrated, was Einstein. He could not accept this. It wasn't that he didn't understand the math. He understood it perfectly, probably better than almost anyone. It was that he believed, deeply and stubbornly, that the universe must be deterministic at its core, that there must be some deeper layer of reality, some hidden variables, that quantum mechanics was simply failing to capture. God does not play dice, he reportedly said to Bohr, and Bohr reportedly replied, Einstein, stop telling God what to do. That exchange, whether it happened exactly that way or not, captures something real about the tension that was building throughout the late 1920s and into the 1930s. And it was this tension, this deep disagreement between two of the greatest minds in physics that would eventually produce the idea of entanglement itself. Because Einstein didn't just sit there and complain. He fought back with thought experiments, clever, precisely constructed arguments designed to show that quantum mechanics must be incomplete. And in 1935, he and two colleagues published a paper that was meant to be the knockout blow, the argument that would finally prove that something was missing from quantum theory. That paper introduced what we now call the EPR paradox, and it's the moment when entanglement stepped out of the shadows and into the spotlight. The thing is, Einstein thought he was exposing a flaw. Instead, he was pointing at something real, something that would turn out to be one of the strangest, most profound features of the physical universe. He just didn't know it yet. So let's talk about that 1935 paper. Einstein wrote it with two younger physicists, Boris Podolsky and Nathan Rosen, both working with him at the Institute for Advanced Study in Princeton. The paper's title was dry and academic, the way physics papers tend to be. Can quantum mechanical description of physical reality be considered complete? But buried inside that bland title was a bomb. And the argument, once you unpack it, is actually pretty elegant. Here's what Einstein, Podolsky, and Rosen, EPR as everyone calls them, were getting at. They started with a reasonable-sounding definition of what it means for a physical theory to be complete. They said, look, if you can predict the value of some physical quantity with absolute certainty, without disturbing the system in any way, then there must be some element of reality corresponding to that quantity. Makes sense, right? If you can know something for sure without even touching it, then that something must actually exist, must be real, independent of whether you bother to look. That's not a radical claim. That's just common sense. Or at least, it feels like common sense. Then they set up a thought experiment. Imagine two particles that interact with each other and then fly apart in opposite directions. Quantum mechanics says that certain properties of these particles become correlated through that interaction. Specifically, EPR focused on things like position and momentum. If you measure the position of particle A, quantum mechanics lets you instantly deduce the exact position of particle B, even though B is far away and you never touched it. Alternatively, if you choose to measure the momentum of particle A instead, you can instantly deduce the exact momentum of particle B. Now, here's the twist. According to Heisenberg's uncertainty principle, which we touched on earlier, you can't know both the position and momentum of a particle simultaneously with perfect precision. That's not a limitation of your instruments. It's supposed to be a fundamental feature of reality. But EPR said, wait a minute. By measuring position on particle A, I can know B's position with certainty. And I could have chosen instead to measure momentum on A, which would have told me B's momentum with certainty. I never touched particle B in either case, so both its position and its momentum must be real, definite quantities, elements of physical reality by our definition. But quantum mechanics says they can't both be definite at the same time. Therefore, quantum mechanics must be incomplete. It's missing something. There must be hidden variables, deeper information that quantum mechanics simply doesn't capture. It's a beautiful argument, really clean logic. And Einstein was genuinely proud of it. He thought this was the one that would finally corner Bohr and the Copenhagen crowd. But there's a subtle assumption buried in there that's easy to miss, and it's the assumption that makes the whole thing so interesting. EPR assumed that measuring particle A can't instantaneously affect particle B when they're far apart. That seems totally reasonable. After all, Einstein's own theory of relativity says that nothing, no signal, no influence, no causal effect, can travel faster than the speed of light. If the two particles are on opposite sides of a laboratory, or opposite sides of a city, or opposite sides of the galaxy, then doing something to one of them shouldn't instantly change anything about the other. Einstein called the alternative spooky action at a distance, Spukhaft Fernwirkung in German, and he meant it dismissively. The idea that measuring one particle could somehow reach across space and instantly affect another particle was, to Einstein, absurd. It violated everything he understood about how the universe works. And this is where entanglement enters the story. Because what quantum mechanics actually predicts, and what experiments would eventually confirm, is that the two particles in the EPR scenario are not independent of each other after they interact. They're entangled. Their properties are correlated in a way that can't be explained by saying each particle secretly carried its own definite values all along. The correlations are too strong, too specific, too perfectly matched to be explained by any local hidden variable theory. And when you measure one particle, the outcome you get is genuinely random, but it's instantly correlated with what you'd find if you measured the other particle, no matter how far apart they are. Let that sit for a moment. Two particles, potentially separated by enormous distances, and yet the result of a measurement on one is immediately linked to the result of a measurement on the other. Not because a signal passed between them, not because they agreed in advance on what answers to give, but because they're described by a single shared quantum state. They're not two separate things anymore, in a very real sense. They're one thing, spread across space. Now, the word entanglement itself, that came from Erwin Schrödinger, who coined the term in response to the EPR paper. Schrödinger read the paper and immediately recognized that Einstein had stumbled onto something genuinely new and deeply weird. He called it Verschränkung in German, which translates to entanglement, and he wrote that he considered it not just one of the interesting features of quantum mechanics, but the characteristic trait of quantum mechanics, the thing that makes it fundamentally different from classical physics. And Schrödinger wasn't someone who was comfortable with quantum weirdness. Remember? This is the same person who came up with the famous cat thought experiment, Schrödinger's cat. specifically to show how absurd quantum superposition sounds when you scale it up to everyday objects. He was deeply uneasy with the implications of the theory he'd helped create, but he recognized that entanglement was central to it. So here's the situation in 1935. Einstein publishes EPR, thinking he's shown that quantum mechanics is incomplete. Bohr responds almost immediately with a paper of his own, same journal, same title, essentially saying Einstein's argument doesn't hold up because the assumption of locality, the assumption that measuring particle A can't affect particle B, isn't justified within the quantum framework. Bohr's response was, well, it was famously difficult to follow. Even physicists who agreed with Bohr admitted that his rebuttal was murky and hard to pin down. But the physics community, by and large, sided with Bohr. The feeling was that Einstein was fighting a rearguard action, clinging to classical intuitions that quantum mechanics had already shown to be inadequate. And for the next couple of decades, that's more or less where things stood. The EPR argument was treated as a philosophical curiosity, not a scientific one. Most working physicists shrugged and got on with using quantum mechanics, which worked spectacularly well for predicting experimental results. The question of whether the theory was complete or whether hidden variables existed underneath, that was seen as metaphysics, not physics. You couldn't test it. It was just a matter of interpretation, of personal taste, of philosophical preference. But here's the thing, and this is really important. That assessment was wrong. The question wasn't untestable. It just took someone brilliantly stubborn to figure out how to test it, and that someone wouldn't come along for almost 30 years. His name was John Stuart Bell, and he was a Northern Irish physicist working at CERN in Geneva. Bell is one of those figures in physics who didn't get nearly enough recognition during his lifetime. He was quiet, thoughtful, deeply principled, and he had this rare ability to cut through philosophical fog and find the hard, mathematical core of a problem. And Bell was unusual among physicists of his generation, in that he actually took the EPR argument seriously. He didn't dismiss it as old-fashioned or philosophical. He genuinely wanted to know, could there be hidden variables? Could Einstein have been right? Bell came at the problem from an interesting angle. He was sympathetic to a hidden variables theory that had been proposed in 1952 by David Bohm, a brilliant and somewhat tragic figure in physics. Bohm had actually managed to construct a version of quantum mechanics that was fully deterministic, with particles having definite positions and momenta at all times, guided by a pilot wave. It reproduced all the predictions of standard quantum mechanics, which should have been a bombshell. Here was exactly what Einstein wanted, a deterministic theory underlying the quantum probabilities. But there was a catch. Bohm's theory was non-local. It required instantaneous influences between distant particles. It had that spooky action at a distance built right into its foundations. Most physicists dismissed it for that reason, and also because, well, Bohm himself had been blacklisted during the McCarthy era, forced to leave the United States because of his political associations, and his work didn't get the attention it deserved, partly for reasons that had nothing to do with physics. Bell studied Bohm's theory carefully and asked a profound question. Is non-locality just a feature of Bohm's particular approach? Or is it unavoidable for any hidden variable theory that reproduces quantum predictions? In other words, could you construct a local hidden variable theory, one without spooky action at a distance, that still matches what quantum mechanics predicts? And in 1964, Bell proved that you can't. That's Bell's theorem, and it's one of the most important results in the history of physics. Full stop. What Bell showed is that any theory based on local hidden variables, any theory where particles carry predetermined values and where no faster-than-light influence exists, must obey certain statistical constraints. These constraints are called Bell inequalities, and quantum mechanics predicts that entangled particles will violate those inequalities. The correlations between entangled particles are stronger than any local hidden variable theory can possibly produce. Think about what that means. Bell didn't just say Einstein's hidden variables idea was unlikely or inelegant. He showed mathematically that there's a hard limit on how correlated two particles can be if they're operating independently with preset instructions, and quantum mechanics blows right past that limit. It predicts correlations that are simply impossible if the particles are just carrying hidden notes in their pockets, so to speak. Now, Bell's theorem is a theoretical result. It tells you what to look for, but it doesn't tell you what nature actually does. For that, you need experiments. And in 1964, the technology to do those experiments didn't quite exist yet. The detectors weren't sensitive enough, the sources of entangled particles weren't reliable enough, and the whole setup required a level of precision that was just barely out of reach. But people started trying, and the story of those experiments, the decades-long effort to actually test Bell's inequality in the real world with real photons and real detectors, is one of the great experimental sagas in all of physics. It involves a young French physicist named Alain Aspect, working in a basement laboratory in the early 1980s, building an experiment that most of his senior colleagues thought was a waste of time. It involves ingenious tricks to close loopholes that skeptics kept pointing out, and it involves results that would eventually earn a Nobel Prize, though not until 2022, nearly 40 years after the key experiments were done. The story of how those experiments unfolded and what they revealed about the nature of reality itself is where things get really fascinating. Because up until this point, everything about entanglement lived in the world of theory, thought experiments, mathematical proofs, philosophical arguments between brilliant people who couldn't actually settle the question by looking at nature. Bell had given the world a recipe. He'd said, here's the test, here's the number, here's the line in the sand. If the correlations come out below this value, Einstein was right, and there are hidden variables pulling the strings behind the scenes. If the correlations come out above it, then quantum mechanics is doing something genuinely strange, something non-local, something that can't be explained by particles carrying secret instructions. But someone had to actually go into a lab and do the experiment. The first serious attempts came in the early 1970s. A physicist named John Clauser, working at UC Berkeley, was one of the first people to take Bell's theorem seriously as something you could actually test. And this is worth pausing on, because in the late 1960s and early 1970s, most physicists considered the foundations of quantum mechanics to be a settled question. The Copenhagen interpretation worked. You could calculate things, predict things, build things. Why would you waste your time on philosophical questions about whether particles had definite properties before you measured them? That was considered, frankly, a little embarrassing, the kind of thing that might derail a young physicist's career. And Clauser was warned about exactly that. His advisors told him it wasn't a productive line of research, but he did it anyway. Clauser, along with Stuart Friedman, performed the first real experimental test of Bell's inequality in 1972. They used pairs of entangled photons, particles of light, produced by exciting calcium atoms. The basic idea was straightforward in concept, even if the execution was fiendishly difficult. You create a pair of entangled photons that fly off in opposite directions. You set up polarization detectors on each side, devices that measure whether the photon's polarization is aligned along a particular angle. And then you measure lots and lots of pairs, varying the angles of the detectors, and you look at the correlations. How often do the two detectors agree? How often do they disagree? And does the pattern of agreement and disagreement match what Bell's inequality allows? Or does it exceed it? Their results favored quantum mechanics. The correlations were stronger than any local hidden variable theory could explain. But, and here's the thing, the experiment had limitations. The detector settings were fixed during each run. They'd set the angles, run the experiment, collect data, then change the angles and run it again. Which meant there was a loophole. A skeptic could argue that maybe the particles somehow knew in advance what angle the detectors were set to. Maybe there was some kind of signal, some kind of communication between the source and the detectors that allowed the particles to coordinate their behavior without any genuine non-locality. It sounds far-fetched, but in physics, if there's a loophole, you have to take it seriously. The whole point of testing Bell's inequality is to rule out local hidden variables, and if your experimental setup leaves a door open, even a tiny, implausible door, then you haven't really closed the case. This particular loophole is called the locality loophole, and closing it would require something clever. You'd need to change the detector settings while the photons were already in flight, so fast that no signal traveling at the speed of light could possibly carry information from one detector to the other in time. The measurement choices on each side would have to be made at the last possible instant, completely independently, so that there's no way the particles or the detectors or anything else in the universe could conspire to fake the correlations. And this is where Alain Aspect enters the story. Aspect was a young French physicist at the Institut d'Optique in Orsay, just south of Paris. In the late 1970s, he started designing an experiment that would address exactly this loophole. He wanted to switch the detector settings so rapidly that the choice on one side couldn't possibly influence the result on the other side, not even in principle. And the way he planned to do it was genuinely ingenious. But first, he did something that tells you a lot about his character and about the culture of physics at the time. Before committing years of his career to this experiment, he traveled to Geneva to meet John Bell himself. He wanted to ask Bell directly whether this experiment was worth doing, and Bell's first question to him was, "Do you have a permanent position?" Aspect said yes, he did, and Bell essentially said, "Good, because if you didn't, this could ruin your career." That's how marginal this line of research was considered. Testing the foundations of quantum mechanics was seen as somewhere between eccentric and professionally suicidal. But Bell was encouraging. He thought the experiment should be done, and he thought Aspect's approach was sound. So Aspect went back to his basement lab in Orsay and spent years building the apparatus. His key innovation was an acoustic optical switch, a device that could redirect each photon to one of two differently oriented polarizers, with the switching happening so fast that the choice was made after the photons had already left the source. The switching happened every 10 nanoseconds or so, and the two detectors were placed far enough apart that light itself couldn't travel from one to the other during the time it took to make a measurement. This meant that when Detector A made its random choice of which angle to measure, Detector B had already committed to its own random choice, with no possibility of communication between them. Whatever correlations showed up in the data couldn't be explained by any signal passing between the two sides. Aspect and his colleagues, Jean Dalibard and Gérard Roget, published their results in 1982. And the results were unambiguous. The correlations between the entangled photons violated Bell's inequality by a wide margin, exactly as quantum mechanics predicted. The statistical significance was overwhelming. Nature was doing something that no local hidden variable theory could account for. Now, you might think that would have settled the debate once and for all. But physics is a cautious discipline, especially when the stakes are this high. And there were other loopholes that Aspect's experiment hadn't fully closed. The biggest one is called the detection loophole, sometimes called the fair sampling loophole, and it's a subtle but important concern. Here's the issue. In Aspect's experiment, and in Clauser's before him, the detectors didn't catch every single photon. Photon detectors in the 1970s and 1980s were far from perfect. They'd miss a significant fraction of the photons that arrived, so you'd only see a subset of the entangled pairs. And a determined skeptic could argue that maybe the detected photons weren't a fair sample. Maybe the ones that got detected were somehow special. Maybe the hidden variables conspired so that only the photons that would violate Bell's inequality happened to reach the detectors, while the ones that would have obeyed the inequality slipped through undetected. It sounds almost absurdly contrived, but again, if you're trying to make a definitive statement about the fundamental nature of reality, you can't leave any door open, no matter how unlikely it seems. Closing the detection loophole required detectors that were efficient enough to catch nearly every particle, and that technology took decades to develop. There were experiments throughout the 1990s and 2000s that chipped away at various loopholes, each one tightening the case. Some experiments closed the locality loophole more rigorously than Aspect had. Others used different types of entangled particles, not photons, but atoms or ions, where the detection efficiency was much higher. But for a long time, no single experiment closed all the major loopholes simultaneously. That changed in 2015, and it happened in a burst. 3 independent groups, working on 3 different continents, each performed what physicists call a loophole-free Bell test. The first was a group led by Ronald Hansen at Delft University of Technology in the Netherlands. Their experiment was remarkable. They used entangled electrons trapped in diamond crystals, separated by 1.3 kilometers, over 3/4 of a mile. The entanglement was established through a clever process called entanglement swapping, where photons emitted by each electron were sent to a central station and measured together, which projected the distant electrons into an entangled state, without them ever directly interacting. The detector settings were chosen using random number generators, and the whole thing was arranged so that the locality loophole and the detection loophole were both closed at the same time. The results? Bell's inequality was violated. Quantum mechanics won again. Within months, groups in Vienna and at the National Institute of Standards and Technology in Boulder, Colorado, published their own loophole-free tests using entangled photons with high-efficiency detectors. Same result. Every time anyone looked, nature behaved exactly as quantum mechanics predicted, and exactly as local hidden variable theories said it couldn't. And here's something that makes this story feel even more poignant. John Bell himself never got to see these definitive experiments. He died in 1990 of a sudden cerebral hemorrhage at the age of 62. He was widely expected to receive a Nobel Prize, and many physicists believe he would have shared the 2022 prize had he lived. That prize went to Alain Aspect, John Clauser, and Anton Zeilinger, 3 experimentalists who had spent their careers testing and extending Bell's theoretical insight. When the Nobel Committee made the announcement, they cited work on experiments with entangled photons, establishing the violation of Bell inequalities and pioneering quantum information science. It was a recognition not just of clever experiments, but of a decades-long campaign to answer one of the deepest questions in physics. And it was a vindication of everyone who'd been told they were wasting their time on foundational questions. So let's take a breath here and think about what all of this actually means. What does the violation of Bell's inequality tell us about the universe? Because the experimental result is clear. Local hidden variables are ruled out. But what replaces them? What's actually going on when two entangled particles, separated by any distance, show these impossibly strong correlations? This is where things get genuinely strange, and where even physicists start to disagree with each other. Because Bell's theorem doesn't tell you exactly what's happening. It tells you what's not happening. It rules out one very intuitive picture of reality, the picture where particles have definite properties all along and just reveal them when measured, like coins that were already heads or tails before you looked. That picture is dead. The experiments killed it. But there are multiple ways to make sense of what's left, and each one requires you to give up something that feels fundamental. One option is to accept non-locality, to say that when you measure one entangled particle, something really does happen to the other one, instantaneously, regardless of distance. The measurement here influences the outcome there. This is the option that bothered Einstein so much, the spooky action at a distance. And it's worth noting that even though it sounds like it should violate special relativity, it doesn't. At least not in any way that lets you send a message faster than light. The correlations are real, but you can't use them to transmit information because the individual measurement results on each side look completely random. It's only when you compare the two sets of results that the correlations appear. So there's no faster-than-light telegraph here. No way to call someone on Mars and have them get the message before a light signal would arrive. The universe seems to have built in a kind of safeguard. The non-locality is real but unusable for communication, which is a deeply weird thing to wrap your head around. Another option is to say that there's no non-local influence at all, but instead, the measurement doesn't just reveal a pre-existing reality. It helps create it. Before you measure an entangled particle, it simply doesn't have a definite polarization or spin. The property comes into existence at the moment of measurement. And because the two particles are described by a single quantum state, the act of measurement on one side instantaneously defines the state on the other side, not by sending a signal, but because they were never really separate to begin with. They're one system, described by one mathematical object, no matter how far apart the particles happen to be. Distance, in some sense, is irrelevant to the quantum state. The entangled pair doesn't live in ordinary three-dimensional space the way we imagine billiard balls do. It lives in a more abstract mathematical space, and in that space, the two particles are right next to each other, always. And then, there's the many worlds interpretation, which takes yet another approach. In that picture, when you measure an entangled particle, the universe splits. Every possible outcome happens, each in its own branch. The correlations between entangled particles are explained not by signals or by the absence of definite properties, but by the structure of how the branches relate to each other. It's a framework that avoids non-locality entirely, but at the cost of accepting an essentially infinite number of parallel universes, which is its own kind of extravagance. Each of these interpretations is consistent with the experimental results. Bell's theorem doesn't choose between them. It just draws a line and says, whatever is going on, it's not local hidden variables. And that's a profound result, maybe one of the most profound in the history of science. It tells us that the universe is, at its most fundamental level, not the way our everyday intuitions suggest. Something about separateness, or about definiteness, or about the nature of reality itself is different from what we assumed. But here's what's really remarkable about the story of entanglement. For decades, it was treated as a philosophical curiosity. Interesting, maybe, but useless. You couldn't do anything with it. It was a feature of quantum mechanics that was fascinating to argue about, but had no practical application. And then, starting in the 1980s and accelerating through the 1990s, people began to realize that entanglement wasn't just a strange property of nature. It was a resource, something you could harness, manipulate, and use to do things that would otherwise be completely impossible. And the person who arguably did more than anyone else to kickstart that revolution was a physicist we haven't talked about yet, a man named Richard Feynman, who in 1981 stood up at a conference and asked a deceptively simple question about whether you could simulate physics with a computer. The answer he arrived at would plant the seed for an entirely new kind of machine, a quantum computer. And the reason Feynman's question mattered so much is that he wasn't just being clever. He was pointing at something genuinely deep about the limits of classical computation, something that connects directly back to everything we've been talking about with entanglement and superposition and the strangeness of quantum mechanics. So here's what Feynman was getting at. Imagine you have a system of, say, 40 quantum particles. Each one can be in a superposition of two states, spin up or spin down, for instance. Now, if you want to describe the full quantum state of that system on a regular computer, you need to keep track of every possible combination of those 40 particles' states, 2 to the power of 40. That's roughly 1 trillion combinations. For each one, you need to store a complex number, an amplitude. So you're looking at 1 trillion complex numbers just to describe the state of 40 little particles. Add a few more particles, and the numbers get absurd. 50 particles, a quadrillion amplitudes, 100 particles. More amplitudes than there are atoms in the observable universe. There is no classical computer, no matter how powerful, that can simulate 100 entangled quantum particles in full generality. The memory requirements alone are impossible. And Feynman looked at this situation and said, essentially, well, nature is doing it. Nature is computing these quantum states effortlessly, all the time, in every atom and molecule. So what if we built a computer that worked the same way nature does? What if instead of trying to simulate quantum physics on a classical machine, we built a machine that was itself quantum mechanical? A machine whose basic units of information weren't classical bits, zeros and ones, but quantum bits, qubits, that could exist in superpositions and, crucially, become entangled with each other. That was the seed. It was 1981, at a conference at MIT, and Feynman was giving one of those talks that only Feynman could give. Playful, provocative, deeply intuitive. He wasn't proposing a blueprint. He wasn't saying, here's how to build one. He was saying, here's why you'd want to, and here's why nothing else will work for simulating quantum systems. And the audience listened, and some of them probably thought it was interesting but impractical, and then they went back to their labs and mostly forgot about it. Because in 1981, nobody had any idea how you'd actually build such a thing. But the idea didn't die. It sat there, quietly, for about a decade. And then in the early 1990s, things started to accelerate. A mathematician at the University of Oxford named David Deutsch had already been thinking along similar lines. Deutsch is a fascinating character, deeply philosophical, a committed many worlds advocate, someone who sees quantum computation not just as a technology, but as evidence for the reality of parallel universes. In 1985, he published a paper describing a universal quantum computer, a theoretical machine that could simulate any physical process, not just quantum ones. It was abstract, mathematical, and at the time, it was mostly of interest to a small community of theorists. But Deutsch had laid down the theoretical foundation. He'd shown that a quantum computer, in principle, could do things a classical computer couldn't. The question was, could it do anything useful? Not just simulate quantum physics, which was interesting but niche, but solve problems that people actually cared about. Problems in cryptography, optimization, search, the kinds of things that drive real-world computing. And this is where a quiet, unassuming mathematician named Peter Shor comes into the story. In 1994, Shor, working at Bell Labs, the same Bell Labs where John Bell had done some of his thinking decades earlier, discovered an algorithm, a quantum algorithm. And it could do something extraordinary. It could factor large numbers exponentially faster than any known classical algorithm. Now, you might be thinking, who cares about factoring numbers? And that's a fair question until you realize that the entire infrastructure of internet security, every time you type a credit card number into a website, every encrypted email, every secure connection your phone makes to a server, almost all of it relies on the assumption that factoring large numbers is really, really hard. The RSA encryption system, which has been the backbone of digital security since the late 1970s, works precisely because if you multiply two large prime numbers together, it's easy to get the product, but going backwards, figuring out which two primes were multiplied, is computationally brutal. A classical computer trying to factor a number with, say, 600 digits would take longer than the age of the universe. That's not a metaphor. That's a real estimate. Shor showed that a quantum computer running his algorithm could do it in a matter of hours, maybe minutes. The implications were staggering. If you could build a large enough quantum computer, you could break essentially all of modern public key cryptography. Every secure transaction, every military communication, every encrypted database, all of it suddenly vulnerable. And here's the thing. Shor's algorithm doesn't work despite entanglement. It works because of entanglement. The qubits in a quantum computer aren't just independently doing their own thing in superposition. They're entangled with each other, and it's that entanglement that allows the algorithm to explore an exponentially large space of possibilities simultaneously and then, through careful interference, constructive and destructive like waves in a pond, extract the right answer with high probability. Without entanglement, you just have a bunch of independent coin flips. With entanglement, you have something qualitatively different, something powerful. Shor's algorithm hit the physics and computer science communities like a thunderbolt. Suddenly, quantum computing wasn't a philosophical curiosity. It was a potential threat to national security. And governments started paying attention. Funding started flowing. And experimentalists, who had been tinkering with individual atoms and photons in their labs for years, suddenly had a very concrete reason to figure out how to control and entangle qubits reliably. But let's not get ahead of ourselves, because around the same time Shor was shaking up cryptography, something equally beautiful was happening on the other side of the quantum information revolution. People were figuring out that entanglement could be used not just for computation, but for communication, in ways that sound like pure science fiction. In 1993, a team of physicists, Charles Bennett, Gilles Brassard, Claude Crepeau, Richard Jozsa, Asher Perez and William Wooters published a paper proposing something called quantum teleportation. And I know, the name sounds ridiculous. It sounds like Star Trek. But what they described is real. It's been demonstrated in laboratories around the world, and it's one of the most elegant uses of entanglement ever conceived. Here's how it works, and I want you to follow this carefully, because it's genuinely beautiful. Say Alice has a qubit, a quantum particle in some unknown quantum state. She doesn't know what state it's in, and she wants to send that exact state to Bob, who's far away. Now, she can't just measure her qubit and send the result, because measuring it would collapse the superposition and destroy the very information she's trying to transmit. She can't copy it either because there's a theorem, the no-cloning theorem, that says you cannot make a perfect copy of an unknown quantum state. It's literally forbidden by the laws of physics. So she's stuck, right? Not if she and Bob share a pair of entangled particles. Here's what Alice does. She takes her mystery qubit and her half of the entangled pair, and she performs a special joint measurement on them. A Bell state measurement, named after the same John Bell, whose theorem we spent so much time with earlier. This measurement entangles her mystery qubit with her half of the shared pair, and it gives her two classical bits of information, just ordinary zeros and ones. She sends those two bits to Bob through a regular channel, a phone call, an email, a carrier pigeon, whatever. And then Bob, using those two bits as instructions, performs one of 4 simple operations on his half of the entangled pair. And when he does, and this is the magical part, his particle is now in exactly the state that Alice's mystery qubit was in originally. The quantum state has been transferred from Alice to Bob without any quantum particle traveling between them. The original state at Alice's end is destroyed in the process. It has to be because of the no-cloning theorem, but it's been perfectly recreated at Bob's end. Think about what just happened. The quantum information didn't travel through the classical channel. Only 2 ordinary bits did, which carry no quantum information on their own. And it didn't travel through the entanglement either, because entanglement alone can't transmit information. We talked about that earlier. It's as if the information was disassembled at one location and reassembled at another, using entanglement as the channel and classical communication as the key. Neither one alone is sufficient. You need both. And the speed of the whole process is limited by the speed of that classical communication. You can't teleport faster than light, so Einstein can rest easy on that front. Quantum teleportation was experimentally demonstrated for the first time in 1997 by Anton Zeilinger's group in Innsbruck, Austria, the same Zeilinger who would later share the 2022 Nobel Prize. They teleported the polarization state of a photon across a laboratory bench. It wasn't teleporting matter. It wasn't teleporting energy. It was teleporting information, the quantum state itself. And since then, teleportation has been demonstrated over longer and longer distances. In 2017, a Chinese team used the Messias satellite to teleport quantum states from a ground station in Tibet to the satellite in orbit, a distance of over 1,400 kilometers. That's quantum teleportation from the surface of the Earth to space. And this isn't just a party trick. Quantum teleportation is a fundamental building block for quantum networks, a future quantum internet where entangled particles are shared between nodes and quantum information can be transmitted securely over long distances. It's also essential for certain approaches to quantum computing, where teleportation is used to move quantum information between different parts of a processor without physically moving the qubits themselves. But here's what I find most beautiful about teleportation and about Shor's algorithm. and about all of these quantum information protocols that emerged in the 1990s. They all depend on entanglement, the very thing Einstein called spooky, the very thing that seemed like a philosophical embarrassment for decades. It turned out that the spookiness wasn't a bug. It was the most valuable feature of quantum mechanics. The thing that made Einstein uncomfortable was precisely the thing that makes quantum technology powerful. And this realization, that entanglement is a resource, something to be quantified, distributed, and consumed, gave birth to an entirely new way of thinking about quantum mechanics, not just as a theory of physics, but as a theory of information. People started asking questions like, how much entanglement does a particular quantum state contain? Can you distill noisy entanglement into pure entanglement? Can you use entanglement to send classical information more efficiently? These questions spawned a whole new field, quantum information theory, that sits at the intersection of physics, mathematics, and computer science. And one of the deepest insights to come out of this field is something that might sound strange at first, but becomes more profound the longer you sit with it. It's the idea that information itself might be physical, not just abstract, not just patterns in a ledger or bits in a computer, but something woven into the fabric of reality at the deepest level. That the laws of physics are, in some sense, laws about what information can and cannot do, what can be copied, what can be transmitted, what can be erased, what can be entangled. And entanglement, in this view, isn't just a weird quantum correlation. It's a fundamental unit of quantum information, as basic as the bit is to classical computing. This perspective has led to some truly extraordinary places, including one of the most surprising connections in all of modern physics, a connection between entanglement and gravity, between quantum information and the geometry of spacetime itself. And the person who arguably opened that door was a theoretical physicist named Juan Maldacena, who in 1997, the same year Zeilinger was teleporting photons in Innsbruck, proposed something called the ADS/CFT correspondence, a conjecture that links quantum theory and general relativity in a way that nobody had quite expected. Maldacena was working at Harvard at the time, still in his late 20s, and he was grappling with one of the hardest problems in theoretical physics: how to reconcile quantum mechanics with general relativity. These two pillars of modern physics, as you probably know, don't play nicely together. Quantum mechanics governs the very small: atoms, photons, electrons. General relativity governs the very large: stars, galaxies, the curvature of space-time around massive objects. Each theory is spectacularly successful in its own domain, but when you try to combine them, when you ask what happens at the center of a black hole, or at the very first instant of the Big Bang, where you need both theories simultaneously, the math breaks down. You get infinities. You get nonsense. And for decades, nobody could figure out how to fix it. What Maldacena proposed was not a full theory of quantum gravity, but something almost as valuable: a dictionary, a way of translating between two seemingly different theories. On one side, you have a theory of gravity in a particular kind of curved spacetime called anti-de Sitter space. That's a spacetime with a specific geometry, sort of like a saddle shape extended into higher dimensions. On the other side, you have a quantum field theory, no gravity at all, living on the boundary of that spacetime, like a hologram projected on the walls of a room. And Maldacena's conjecture, which has since been supported by an enormous amount of evidence, though never rigorously proven, says these two descriptions are exactly equivalent. Everything that happens in the gravitational bulk, stars forming, black holes evaporating, gravitational waves rippling through space, has a precise translation into the language of the boundary theory, which is a quantum theory without gravity, and vice versa. Now you might be thinking, that's fascinating, but what does this have to do with entanglement? And here's where it gets really beautiful. As physicists started exploring the ADS/CFT correspondence in the years after Maldaceno's paper, they began to notice something remarkable. The geometry of the bulk spacetime, the actual shape of space, the distances between points, the curvature, seemed to be related to the pattern of entanglement in the boundary theory. Regions of the boundary that were highly entangled with each other corresponded to regions of the bulk that were close together in space. Regions with little entanglement corresponded to regions that were far apart. It was as if entanglement was stitching space-time together, as if the very fabric of space emerged from quantum correlations. This idea was sharpened dramatically in 2006 by a physicist named Shinsei Ryu and his collaborator, Tadashi Takayanagi, who were working at the University of California, Santa Barbara. They proposed a precise formula, now called the Ryu-Takayanagi formula, that relates the entanglement entropy of a region in the boundary theory to the area of a particular surface in the bulk spacetime. Think about what that means. Entanglement entropy is a purely quantum information concept. It measures how entangled one part of a quantum system is with the rest, and the area of a surface in the bulk is a purely geometric concept. It's about the shape of space-time, and Ryu and Takayanagi showed that these two things are equal, up to some constants. It's almost like saying, the amount of quantum correlation between two regions of a hologram determines the literal distance between corresponding points in the higher dimensional space that the hologram describes. Let that sit for a moment. Because this is one of those ideas that sounds technical at first, but becomes genuinely mind-bending when you let it sink in. It suggests that space, the thing you move through, the distance between your bed and the door, the gap between Earth and the moon, might not be fundamental. It might be emergent. It might arise from something deeper, and that deeper something might be entanglement. The quantum correlations between microscopic degrees of freedom woven together in just the right pattern could be what gives rise to the smooth, continuous space-time we experience every day. And this isn't just poetic speculation. Physicists have shown that if you take the boundary theory and you systematically reduce the entanglement, if you disentangle parts of the quantum system, the corresponding bulk spacetime develops cracks, tears, disconnections. The geometry falls apart. It's as if you're pulling threads out of a fabric, and the fabric starts to come undone. Mark van Ramsdonk, a physicist at the University of British Columbia, wrote a beautiful paper in 2010 making exactly this argument. He showed that in the ADS/CFT framework, a completely unentangled boundary state corresponds to a completely disconnected bulk space-time, just separate, isolated chunks of space with no way to get from one to another. Entanglement in this picture is literally the glue that holds space together. Here's the thing that makes this so profound for our story. Remember how Einstein, back in 1935, dismissed entanglement as spooky action at a distance? He thought it was a sign that quantum mechanics was incomplete, that something was missing from the theory. He spent the last decades of his life searching for a unified theory that would connect quantum mechanics and gravity, and he never found it. And now, 8 decades later, physicists are discovering that entanglement, the very phenomenon Einstein found so troubling, might be the key to exactly the unification he was looking for. The bridge between quantum mechanics and general relativity might be built out of entanglement itself. There's a deep irony there, and also something kind of beautiful about it. The thing he rejected might be the thing that completes his life's work. In 2013, Maldacena teamed up with Leonard Susskind, another giant of theoretical physics based at Stanford, to push this idea even further. They proposed a conjecture that goes by the catchy name ER equals EPR. Now, ER refers to Einstein-Rosen bridges, which are what physicists call wormholes, those hypothetical tunnels through space-time that connect two distant black holes. Einstein and his collaborator Nathan Rosen described these in a 1935 paper. And EPR, of course, refers to the Einstein-Podolsky-Rosen paper from the same year, the one about entanglement. So the ER equals EPR conjecture says that these two things, which Einstein worked on in the same year and probably never imagined were related, are actually the same thing. Every pair of entangled particles is connected by a tiny, microscopic wormhole. And every wormhole, conversely, is a manifestation of entanglement between the quantum states on either end. Now, to be clear, this is still a conjecture. It hasn't been proven, and the wormholes in question aren't the kind you could send a spaceship through. They're not traversable in any practical sense. But the conceptual implications are staggering. It means that the spooky connection between entangled particles, the thing that bothered Einstein so much, might literally be a bridge through space-time. Not a signal traveling faster than light, not any violation of relativity, but a geometric connection, a tiny thread of space-time linking two distant points. The non-locality isn't spooky at all in this view. It's just geometry. And this brings us to a question that's been simmering underneath everything we've talked about tonight. A question that physicists are still wrestling with right now, in offices and on chalkboards and in late-night conversations at conferences. The question is, what is entanglement, really? Not just mathematically. We know the math. Not just operationally. We know how to create it, measure it, use it. But what is it telling us about the nature of reality? Because here's the landscape as it stands. If you follow the thread from EPR through Bell, through the experiments of Clauser and Aspect and the loophole-free tests of 2015, you arrive at a clear conclusion. Entanglement is real. It's non-local in some meaningful sense, and no theory based on local hidden variables can reproduce its predictions. But that still leaves open the question of interpretation. What's actually happening when two entangled particles are measured far apart, and their results are correlated in ways that can't be explained by any shared local cause? The Copenhagen interpretation, which we talked about earlier, Bohr's view, essentially says, don't ask. The quantum state isn't a description of reality. It's a tool for predicting measurement outcomes. Entanglement just means the predictions for the two particles are correlated. There's no deeper story. This works fine pragmatically, but it leaves a lot of people unsatisfied. It feels like it's dodging the question. The many worlds interpretation, which was proposed by Hugh Everett in 1957, and which we haven't really discussed yet, takes a radically different approach. In this view, every quantum measurement causes the universe to branch. When you measure one of the entangled particles and get spin up, there's another branch of reality where you got spin down, and in that branch, your distant friend who measures the other particle gets the correspondingly different result. There's no non-local influence at all, because both outcomes happen, just in different branches. The correlations are explained by the structure of the branching, not by any signal between the particles. It's an elegant solution in some ways, but it requires you to accept the existence of an unimaginably vast number of parallel universes, which is, well, it's a lot to take on board. Then there's the pilot wave theory we mentioned earlier, Bohm's approach, where particles have definite positions guided by a wave that is explicitly non-local. This gives you a clear physical picture, but at the cost of accepting that influences really do propagate instantaneously across space. They just happen to be structured in a way that you can never use them to send a signal faster than light. And there are relational interpretations, and cubism, and collapse theories, and a dozen other frameworks, each with their own strengths and their own uncomfortable trade-offs. What's remarkable is that all of these interpretations agree on the predictions. They all reproduce the same experimental results. They all predict the same Bell inequality violations, the same teleportation outcomes, the same behavior of quantum computers. The physics is settled. What's not settled is the story we tell about the physics. And that might seem like a philosophical luxury. Who cares about interpretation when the equations work? But the ER equals EPR conjecture, and the whole entanglement spacetime connection suggests that interpretation might actually matter for making progress. Because if entanglement really is the fabric of spacetime, then understanding what entanglement is, really deeply at a foundational level, might be the key to understanding what spacetime is. And that could lead to new physics, new predictions, new experiments. So the field is alive with this tension, this productive uncertainty. And meanwhile, on a completely different front, engineers and experimentalists are taking entanglement out of the realm of philosophy and into the realm of technology. Because while theorists are debating whether entangled particles are connected by wormholes, other teams are building machines that use entanglement to do things that would have seemed like science fiction just a few decades ago. And one of the most ambitious of these efforts, one that could genuinely change the world you live in, is the race to build a practical, large-scale quantum computer. We touched on Shor's algorithm earlier and Deutsch's theoretical framework, but the actual engineering challenge of building these machines is something else entirely. Because here's the thing about quantum computers. The idea is elegant, almost deceptively simple when you hear it described in a lecture. But the moment you try to actually build one, you run headfirst into some of the most brutal engineering problems humans have ever faced. And the reason comes back to something we've been circling around this whole time: the extraordinary fragility of quantum states, and especially of entanglement. Let's start with the basic challenge. A classical computer, the kind in your phone or your laptop, stores information in bits. Each bit is either a 0 or a 1. Simple, robust, easy to copy, easy to store. You can write a bit onto a magnetic disk and come back 100 years later and it's still there. Quantum computers use qubits, quantum bits, and a qubit can be in a superposition of 0 and 1 simultaneously. That's where the power comes from. But more importantly, and this is the part that connects to everything we've been talking about, the real computational advantage of a quantum computer comes from entanglement between qubits. When you entangle multiple qubits together, the information isn't stored in any individual qubit. It's stored in the correlations between them, in the relationships, and the number of these correlations grows exponentially with the number of qubits. 2 entangled qubits can encode information across 4 possible states. 3 qubits, 8 states. 50 qubits, and you're dealing with more than a quadrillion simultaneous correlations. That's the exponential advantage that makes quantum computers theoretically capable of solving certain problems that would take classical computers longer than the age of the universe. But, and this is a very big but, those correlations, those entangled states, are unbelievably delicate. Remember how we talked about measurement collapsing quantum states? Any interaction with the environment, a stray photon, a vibration in the table, a tiny fluctuation in temperature, counts as a kind of measurement. The environment is constantly trying to look at your qubits, and every time it succeeds, it destroys a little bit of the entanglement you've so carefully built up. This process has a name. It's called decoherence. And decoherence is the single biggest enemy of quantum computing. Think of it this way. Imagine you're trying to balance a coin on its edge on a table. That's your qubit in superposition. Now imagine the table is on a ship in a storm. That's decoherence, the constant buffeting of the environment trying to knock your coin flat, trying to force it into a definite state of heads or tails. A classical bit is like a coin that's already lying flat. It doesn't care about the storm, but a qubit needs to stay balanced on that edge long enough for you to perform your computation, and that's extraordinarily hard to arrange. The first serious attempts to build physical qubits started in the late 1990s, after Shor's algorithm made it clear that quantum computing wasn't just a theoretical curiosity. It was a potential threat to every encryption system on the planet, and immediately the community ran into the decoherence problem. Different groups tried different physical systems. Some used trapped ions, individual atoms suspended in electromagnetic fields, manipulated with laser beams. Others tried nuclear magnetic resonance, using the spins of atomic nuclei in molecules. Others explored photons, the particles of light. And starting around the late 1990s and early 2000s, a group at Yale, led by Robert Scholkopf and Michel Devoret, began developing what would become the dominant approach: superconducting qubits. Superconducting qubits are tiny circuits made of superconducting metal, usually aluminum, cooled to temperatures colder than outer space. We're talking about 15 millikelvin, 15 thousandths of a degree above absolute zero. At those temperatures, the electrical resistance of the circuit drops to zero, and quantum effects become visible at the scale of the whole circuit. The qubit isn't a single atom. It's a macroscopic piece of metal, maybe a millimeter across, behaving quantum mechanically. And the key component is something called a Josephson junction, named after Brian Josephson, who predicted it in 1962 when he was just a 22-year-old graduate student at Cambridge. A Josephson junction is an incredibly thin insulating barrier between two superconductors, and quantum mechanical tunneling across that barrier creates an energy level structure that mimics a two-level quantum system, a qubit. Here's what's wild about this. You're taking a macroscopic electrical circuit and coaxing it into behaving like a single quantum particle. It's as if you took a grandfather clock and somehow made it exhibit the same quantum weirdness as an electron. And the reason you have to cool it down so far is precisely because of decoherence. At room temperature, thermal vibrations would destroy the quantum state in nanoseconds. At 15 millikelvin, you can keep the qubit coherent for maybe 100 microseconds, 100 millionths of a second. That doesn't sound like much, but it's long enough to perform hundreds or even thousands of quantum operations, called gates, before the state decoheres. And that window is everything. Now, building a single qubit is hard enough, but the whole point of quantum computing is entangling many qubits together, and this is where the engineering becomes truly formidable. You need to be able to create entanglement between specific pairs of qubits on demand, perform precise operations on those entangled states, and do it all before decoherence wipes everything out. It's like conducting an orchestra where every instrument is made of soap bubbles, and a single wrong breath pops the whole thing. Google made headlines in 2019 when their Sycamore processor, with 53 superconducting qubits, performed a specific calculation in about 200 seconds that they claimed would take the world's fastest classical supercomputer 10,000 years. They called it quantum supremacy, the point where a quantum computer does something no classical computer practically can. IBM pushed back on that claim, arguing their classical supercomputer could do it in a couple of days with better algorithms, not 10,000 years. The debate got heated. But either way, the demonstration showed that these machines could do something genuinely different from classical computers. The entanglement was real, it was engineered, and it was producing results. But here's the thing that keeps quantum computing researchers up at night. And this connects beautifully to the theoretical work we talked about earlier. Those 53 qubits, they're noisy. Every gate operation has a small error rate, maybe 0.5% or 1%. That sounds tiny, but when you're chaining together thousands of gates across dozens of entangled qubits, those errors compound catastrophically. It's like a game of telephone where each person slightly garbles the message. By the end, you've got nonsense. The solution, in principle, was worked out theoretically in the mid-1990s by Peter Shor himself and independently by Andrew Steen and others. It's called quantum error correction, and it's one of the most beautiful ideas in all of computer science. The basic concept is this. You use many physical qubits to encode a single logical qubit. The extra qubits act as a kind of safety net, constantly checking for errors and correcting them without ever directly measuring the logical qubit state, because measuring it would destroy the superposition. It's like proofreading a book without ever reading the words, only checking the patterns of ink on the page. The most promising error correction scheme is called the surface code, developed largely by Alexei Kitaev and later refined by many others. In the surface code, you arrange physical qubits in a two-dimensional grid, and the logical information is stored not in any individual qubit, but in the topological properties of the entanglement pattern across the whole grid. The word topological is important here. It means the information is protected by the global structure of the entanglement, not by any local property. It's like tying a knot in a rope. You can jostle the rope, wiggle it, even stretch it, and the knot is still there. The only way to destroy the information is to undo the knot itself, which requires a specific, large-scale disruption that random noise is unlikely to produce. But the cost of this protection is staggering. Current estimates suggest you might need somewhere between 1,000 and 10,000 physical qubits to encode a single error-corrected logical qubit, and to run Shor's algorithm to break RSA 2048 encryption, the thing that got governments and intelligence agencies interested in quantum computing in the first place. You'd need on the order of several thousand logical qubits, which means you'd need millions of physical qubits, all entangled, all operating coherently, all at 15 millikelvin. As of right now, the largest quantum processors have a few thousand physical qubits. IBM's Condor chip, released in 2023, has 1,121 superconducting qubits. Google's latest systems are in a similar range. So we're still orders of magnitude away from the kind of fault-tolerant, error-corrected quantum computer that could break encryption or simulate complex molecules. And yet, and this is what makes the field so exciting, the progress is real, and it's accelerating. In 2023, Google's team demonstrated that their surface code implementation actually worked. that adding more physical qubits genuinely reduced the logical error rate, crossing a critical threshold that theorists had predicted, but no one had achieved experimentally. That was a landmark moment. It showed that the path to fault-tolerant quantum computing isn't just theoretical. It's an engineering problem. An incredibly hard engineering problem, maybe the hardest engineering problem humans have ever attempted, but an engineering problem nonetheless. And quantum computing isn't the only technology riding on entanglement. There's a whole parallel effort in quantum communication and quantum networking that's arguably even closer to practical deployment. Remember the quantum teleportation experiments we talked about? Zeilinger's team teleporting photon states across the Danube, the Chinese satellite Meitius distributing entangled photons across 1,200 kilometers. Those experiments weren't just demonstrations of fundamental physics. They were prototypes for something called a quantum internet. The idea is to connect quantum computers and quantum sensors together using entanglement as the communication channel. And the security guarantees are extraordinary because of the no cloning theorem, because any eavesdropper necessarily disturbs the quantum state. You can build communication systems that are provably secure, not just computationally secure, but secure according to the laws of physics themselves. China has been particularly aggressive in this space. They've built a 2,000-kilometer quantum key distribution network connecting Beijing to Shanghai, combining ground-based fiber optic links with satellite-based entanglement distribution. It went operational in 2017. Europe has its own quantum communication infrastructure initiative. The United States launched its National Quantum Internet Blueprint in 2020. And all of these systems, every single one, depend on the controlled generation, distribution, and measurement of entangled particles. Entanglement isn't just a curiosity anymore, it's infrastructure. But there's another application that I find even more fascinating, partly because it's less well known, and partly because it connects back to something deeply fundamental about what entanglement tells us about the nature of reality. And that's quantum sensing. The idea is beautifully simple. Because entangled particles are correlated more strongly than any classical system allows, you can use them to make measurements with a precision that would be literally impossible otherwise. There's a fundamental limit in classical measurement called the shot noise limit. It comes from the fact that you're measuring with discrete particles, photons, or atoms, and the statistical fluctuations set a floor on your precision. But with entangled particles, you can beat that limit. You can reach what's called the Heisenberg limit, which scales much more favorably with the number of particles you use. Gravitational wave detectors like LIGO already use a form of this. They inject squeezed light, which is a type of entangled photon state, into their interferometer arms to push their sensitivity beyond what classical light allows. And that extra sensitivity is part of what made it possible to detect gravitational waves in the first place back in 2015. So entanglement isn't just helping us understand gravity theoretically through ER equals EPR. It's literally helping us detect gravitational waves experimentally. And there are teams working on entanglement-enhanced atomic clocks, entanglement-enhanced magnetometers for medical brain imaging, entanglement-enhanced GPS systems. The precision gains are not incremental. They're qualitative jumps in what's measurable. Things that were invisible to classical instruments become visible when you harness entanglement as a resource, so you can see how the story has evolved. What started as Einstein's discomfort with a theoretical prediction, this spooky action at a distance that he was sure indicated a flaw in quantum mechanics, has become the foundation of an entirely new technological paradigm. And the irony keeps deepening, because the very phenomenon Einstein tried to use to disprove quantum mechanics is now being used to build the most sophisticated machines humanity has ever created. Machines that exploit the exact correlations Einstein found so troubling. But there's one more piece of this story that I want to spend some time with, because it brings everything full circle in a way that I think is genuinely beautiful. And it has to do with a question that sounds almost too simple to be profound. What happens to entanglement when things get really, really complicated? Not complicated in the sense of hard to build, but complicated in the sense of many particles interacting in messy, chaotic ways. Because it turns out that the behavior of entanglement in complex quantum systems, the way it grows, the way it spreads, the way it scrambles information, connects to some of the deepest questions in physics. Questions about black holes, about the arrow of time, about why the universe looks classical even though it's fundamentally quantum. And the person who kicked off this whole line of thinking was, of all people, a string theorist named Patrick Hayden, working with a physicist named John Preskill, and their investigation into something that sounds almost whimsical but turns out to be deadly serious. A thought experiment about how quickly a black hole can process quantum information. They called it the black hole as a mirror, and the question they asked was this: if you throw a quantum bit of information into a black hole, how long do you have to wait before that information comes back out, encoded in the Hawking radiation the black hole emits? And the answer they found in a 2007 paper was shockingly fast, almost as fast as the laws of physics could possibly allow. Now, to understand why that's such a big deal, you need to step back and think about what a black hole does to information. And this connects to one of the longest-running arguments in theoretical physics, a fight that lasted decades and involved some of the biggest names in the field. Stephen Hawking, in 1974, showed that black holes aren't actually perfectly black. They emit radiation, what we now call Hawking radiation, because of quantum effects near the event horizon. Pairs of virtual particles pop into existence, and sometimes one falls in while the other escapes. The black hole slowly evaporates, losing mass over unimaginably long timescales. But here's the problem Hawking identified, and it's a deep one. If the black hole eventually evaporates completely, what happens to all the information about everything that fell in? The quantum states of every particle, every bit of data, every entangled pair. Does it all just vanish? Hawking initially said yes. The information is destroyed, gone forever. And that horrified a lot of physicists, because one of the bedrock principles of quantum mechanics is unitarity, the idea that information is never truly lost. You can scramble it, you can spread it around, you can make it practically impossible to recover, but it's always there in principle. Quantum mechanics is, at its heart, reversible. Every process can in theory be run backward. If black holes destroy information, that breaks quantum mechanics at a fundamental level. This became known as the black hole information paradox, and it consumed theoretical physics for the better part of 30 years. On one side, you had Hawking saying information is destroyed. On the other, you had people like Leonard Susskind and Gerard 't Hooft arguing that the information must somehow be preserved, encoded in the Hawking radiation in some incredibly subtle way. And in 2004, Hawking himself conceded. He came around to the view that information is preserved, that it does come back out. He even paid off a bet he'd made with John Preskill, gave him a baseball encyclopedia, which was Hawking's way of saying, "Here, have some information." But conceding that information comes out is very different from explaining how it comes out. And that's where Hayden and Preskill's work becomes so fascinating. They asked a very specific version of the question. Imagine a black hole that's already been evaporating for a long time. It's already radiated away more than half its original entropy. It's an old black hole, in a sense. Now you throw one qubit into it. One single quantum bit of information. How long before that qubit's information shows up in the Hawking radiation? The naive expectation might be that you'd have to wait a very long time. After all, the black hole is this incredibly complex system with an enormous number of internal degrees of freedom. The information should get lost in there, buried deep, mixed up with everything else. It should take ages to come back out. But Hayden and Preskill showed that for an old black hole, one that's past the halfway point of its evaporation, the information comes out almost immediately, in a time proportional to the logarithm of the number of qubits in the black hole. And logarithmic scaling is fast. Absurdly fast. If the black hole has a trillion degrees of freedom, the logarithm of that is still just a modest number. The information bounces back out almost as quickly as it goes in, and the reason this happens has everything to do with entanglement. By the time a black hole is old, past its halfway point, the Hawking radiation it's already emitted is highly entangled with what's left inside. The interior and exterior are connected by an enormous web of quantum correlations. So when you throw in a new qubit, the black hole's internal dynamics scramble it, mix it up with everything else. And because of all that pre-existing entanglement between the inside and outside, the scrambled information almost immediately shows up in the correlations of the outgoing radiation. The black hole acts like a mirror. It reflects quantum information back at you, just in a highly scrambled form. And here's where a concept called quantum scrambling becomes central. Scrambling is different from just randomizing. When a quantum system scrambles information, it doesn't destroy it. It spreads it out across the entire system in such a way that you can't recover it by looking at any small subsystem. You'd need access to nearly all the degrees of freedom to piece it back together. Think of it like this. Imagine you have a drop of ink and you put it in a glass of water and stir. After enough stirring, the ink is everywhere. You can't point to any one spot and say, the ink is here. But the ink isn't gone. It's distributed. Quantum scrambling is like that, but more extreme, because it involves entanglement. The information from your original qubit becomes entangled with everything else in the system, spread across an exponentially complex web of correlations. And what Hayden and Preskill showed is that black holes are the fastest scramblers in nature. They scramble information as quickly as the laws of physics allow. This idea was formalized further by Sakino and Suskind, who in 2008 conjectured what they called the fast scrambling conjecture. That black holes scramble in a time proportional to the logarithm of their entropy, and that no physical system can scramble faster than that. The logarithmic timescale is the fundamental speed limit for scrambling. Now, you might be wondering, this is all very interesting for people who think about black holes, but does it connect to anything else? And the answer is yes, beautifully. Because scrambling isn't just a black hole phenomenon. It happens in any complex quantum system where many particles interact strongly. It happens in quantum computers. It happens in exotic materials. It even happens in systems that physicists use to model quantum chaos. And studying scrambling has become one of the most active areas in physics, precisely because it sits at the intersection of quantum information, quantum gravity, and condensed matter physics. One of the key tools that emerged from this work is something called an out-of-time order correlator, usually abbreviated OTOC. It's a mathematical quantity that measures how quickly information spreads through a quantum system. The name sounds intimidating, but the idea is actually quite intuitive. In a normal correlation, you ask how two measurements at the same time relate to each other. In an out-of-time order correlator, you essentially ask, if I perturb the system at one point, how quickly does that perturbation affect a measurement somewhere else? It's like the quantum version of the butterfly effect. And when the OTOC decays quickly, that tells you the system is scrambling fast. What's remarkable is that researchers have actually measured these things in the lab. In 2016 and 2017, groups using trapped ions and nuclear magnetic resonance systems were able to observe signatures of quantum scrambling experimentally. They could watch information that started localized in one part of a quantum system spread out and become delocalized across the whole thing. And the scrambling happened in ways that matched the theoretical predictions beautifully. And this connects back to something we touched on earlier, the question of why the universe looks classical. Why, if everything is fundamentally quantum, if superposition and entanglement are the basic rules, does your coffee cup not appear to be in two places at once? Part of the answer is decoherence, which we talked about, the environment constantly interacting with quantum systems and destroying their coherence. But scrambling adds another layer to that story. In a complex system with many interacting parts, quantum information doesn't just decohere, it scrambles. It spreads out so thoroughly, so quickly, that for all practical purposes, the information about the original quantum state becomes inaccessible. Not destroyed, just hidden. Buried in correlations that span the entire system. And that's a key insight. Classicality isn't just about losing coherence with the environment. It's about the internal dynamics of complex systems spreading quantum information so widely that no local measurement can detect it. This idea has profound implications for how we think about thermalization, the process by which a quantum system reaches thermal equilibrium. When you put an ice cube in warm water, it melts, and eventually the whole glass reaches a uniform temperature. That's thermalization. But from a quantum mechanical perspective, what's actually happening? The quantum information in the ice cube's initial state isn't disappearing. It's scrambling. It's spreading out across all the water molecules, all their vibrations, all their entangled correlations, until it's effectively invisible. The system looks thermal, random, featureless, uniform, not because information has been lost, but because it's been scrambled beyond any practical hope of recovery. And here's what's really beautiful about this. It connects the arrow of time. The fact that we experience time moving in one direction, from past to future, from order to disorder, to the growth of entanglement. As a quantum system evolves, entanglement grows. Information scrambles. And that growth of entanglement, that spreading of quantum correlations, is what we perceive as the increase of entropy. The second law of thermodynamics, entropy always increases, might, at the deepest level, be a statement about how entanglement spreads through quantum systems. Think about what that means for a moment. The arrow of time, one of the most fundamental features of our experience. The reason you remember yesterday but not tomorrow, the reason eggs break but don't unbreak, might ultimately be a consequence of entanglement. Of the same phenomenon Einstein called spooky. The same correlations that seemed so paradoxical in 1935 might be the reason time has a direction. And this is where the story starts to feel almost impossibly interconnected. Because remember, the ER equals EPR conjecture. The idea that entanglement and wormholes might be the same thing? If entanglement is also what gives rise to the arrow of time, and if entanglement is what holds space-time together, then you're looking at a picture where quantum correlations aren't just one feature of reality among many. They might be the feature, the thread that connects space, time, gravity, thermodynamics, and information into a single coherent framework. Now, we're deep into speculative territory here, and I want to be honest about that. These are ideas that the best physicists in the world are actively working on, arguing about, testing against each other. None of this is settled. But the direction of the conversation is remarkable, and it all traces back, every thread of it, to that strange property of quantum mechanics that Schrödinger named in 1935, that Einstein tried to use as a reductio ad absurdum, that Bell showed was real, that aspect confirmed in a laboratory, that engineers are now harnessing to build computers and communication networks. Which brings us to something I think is worth spending a little time with, because it's the kind of question that tends to come up when you've been thinking about all of this for a while, lying here in the dark, letting these ideas wash over you. And the question is, what does entanglement actually tell us about the nature of reality? Not what does it let us build, not what equations describe it, but what does it mean? What kind of universe are we living in? If entanglement is real, what kind of universe do we inhabit if the most fundamental thing about it isn't particles, isn't forces, isn't even space or time, but correlations? Relationships between things that somehow run deeper than the things themselves? Let's sit with that for a moment, because it's a genuinely strange idea, and it deserves a little breathing room. Think about how we normally picture the world. You imagine objects, solid, separate, located somewhere specific. A rock is here. The moon is there. You are in your bed, and I'm wherever I am. And there's space between us, and the things in that space are distinct from each other. That's the classical picture. It's the picture Newton gave us, more or less. A universe made of stuff, arranged in space, evolving through time, and the stuff comes first. Space is the stage. Time is the clock, and the objects are the actors. But entanglement quietly undermines that picture in a way that's hard to fully appreciate until you've followed the whole story the way you have tonight. Because what entanglement tells us is that you can't always describe the parts of a system independently. Two particles can be in a state where the whole has a definite description, but the individual pieces don't. The information isn't in the particles, it's in the relationship between them. And that's not a metaphor. That's the math. The quantum state of the pair is well defined. The quantum states of the individuals, taken separately, are not. The correlation is more real, in a precise technical sense, than the things being correlated. Now, you might say, okay, that's weird, but it's just a feature of tiny quantum systems. Particles are strange. We knew that. But here's where the last few decades of theoretical physics have pushed the strangeness to a whole new level. Because if the ideas we've been exploring tonight are on the right track, if entanglement really does give rise to space-time geometry, if the ER equals EPR conjecture captures something true, if the connectivity of space itself is a manifestation of quantum correlations, then it's not just particles that are made of relationships. It's space. It's the very stage on which everything happens. The stage isn't fundamental. The correlations are, and the stage emerges from them. This is such a radical inversion of how we normally think about physics that it's worth saying it one more time, slowly. In the traditional picture, space exists, and then things in space can become entangled. In the emerging picture, entanglement exists, and then space arises because of it. The correlations come first. Geometry is derived. And if that's true, then asking, how can two particles be correlated across a huge distance, is actually asking the question backwards. The distance itself is a consequence of how much, or how little, entanglement there is. Highly entangled regions are close together. Weakly entangled regions are far apart. Distance is entanglement, seen from another angle. I want to be careful here, because this is the kind of idea that can sound like mysticism if you're not precise about it. And it's not mysticism. It's a concrete research program with equations and predictions, and people spending their careers trying to make it rigorous. The Ryu-Takayanagi formula we talked about earlier, the one that relates the entanglement entropy of a boundary region to the area of a surface in the bulk spacetime, that's a precise, calculable relationship. Van Ramsdonk's thought experiment about cutting entanglement and watching spacetime pinch off, that's grounded in specific mathematical frameworks. The ER equals EPR conjecture from Maldacena and Susskind. That's a precise claim about the equivalence of two well-defined structures. These aren't vague gestures. They're attempts to build a new foundation for physics, one where quantum information is the bedrock. And here's what I find quietly astonishing about all of this. The whole journey, from Planck's desperate hypothesis in 1900, through Einstein's photoelectric effect, through Bohr's atom, through the wild debates of the 1920s and 30s, through EPR and Bell and aspect and all those beautiful experiments. The whole journey has been one of gradually realizing that quantum mechanics isn't just a theory about small things. It's a theory about information, about what can be known, what can be correlated, what can be communicated, and what the limits of all those things are. And entanglement sits right at the heart of that realization, because it's the most purely informational phenomenon in all of physics. There's no force being transmitted. There's no signal. There's no mechanism in the classical sense. There's just correlation. Pure, irreducible, non-local correlation. And somehow, that's enough to build a universe out of. Now, there's a beautiful irony in all of this that I think Einstein would have appreciated, even if he might not have liked it. Einstein spent the last decades of his life searching for a unified field theory, a single framework that would bring together gravity and quantum mechanics and electromagnetism into one elegant picture. He never found it. He died in 1955 with pages of unfinished calculations on his desk. And the tool he dismissed, entanglement, the thing he called spooky, the thing he was sure indicated that quantum mechanics was incomplete, that tool might turn out to be the key to the unification he was looking for. Not a unified field theory exactly, but a unified information theory. A framework where space-time, gravity, thermodynamics, and quantum mechanics all emerge from the same underlying structure of quantum correlations. If that's not poetic, I don't know what is. But let me bring this back down to earth a little, because I think it's important to be honest about where we actually stand. As of right now, and by right now I mean the mid-2020s, we don't have a complete theory of quantum gravity. We have incredibly suggestive hints. We have the ADS/CFT correspondence, which works beautifully in a specific kind of space-time that isn't quite the one we live in. We have the Ryu-Takayanagi formula and its generalizations. We have ER equals EPR. We have tantalizing connections between entanglement, scrambling, black holes, and the emergence of classical reality. But we don't have the final answer. Nobody does. And anyone who tells you they do is either confused or selling something. What we do have is something that might be even more valuable at this stage. We have the right questions. And that matters enormously in physics. For decades, the question was, how do you quantize gravity? How do you take Einstein's smooth, curved spacetime and make it compatible with the discrete, probabilistic world of quantum mechanics? And people made progress on that question, real progress. String theory, loop quantum gravity, various other approaches. But the entanglement revolution has reframed the question in a way that feels deeper. It's not just, how do you quantize gravity? It's, how does gravity emerge from quantum information in the first place? And that shift in perspective, from trying to quantize spacetime to trying to derive spacetime, might be the most important conceptual advance in theoretical physics in a generation. There's a phrase that the physicist John Wheeler coined back in the 1980s and 90s that keeps coming back to me as we talk about all of this. Wheeler, who was Feynman's doctoral advisor, by the way, and one of the great creative minds of 20th century physics, Wheeler proposed a slogan, "It from bit." The idea that every physical thing, every it, ultimately derives its existence from information, from bits. He was ahead of his time, honestly. When he first started saying this, most physicists thought it was a charming but slightly eccentric philosophical position. But look at where the field has gone. Quantum information theory, holographic entanglement entropy, the idea that space-time is woven from quantum correlations. Wheeler's slogan looks less and less like philosophy and more like a research program. And if we were to update it for the quantum era, we might say something like, it from qubit, everything from quantum information, everything from entanglement. And, lying here thinking about this, there's something deeply comforting about that idea, even if it sounds abstract, because it means the universe isn't fundamentally made of cold, dead matter bouncing around in empty space. It's made of connections, relationships, information. The universe, at its deepest level, is relational. Nothing exists entirely on its own. Everything is defined, at least in part, by its correlations with everything else. And that's not a spiritual claim. It's what the equations say. It's what the experiments confirm. It's what Bell proved, and Aspect measured, and Zeilinger teleported, and the teams in Delft and Vienna and Boulder verified when they closed every loophole they could think of. I think there's also something worth noting about how this story reflects the way science actually works, which is nothing like the clean, logical progression you see in textbooks. The real story is messy. It's full of wrong turns and arguments, and people being right for the wrong reasons and wrong for the right reasons. Einstein was wrong about entanglement being evidence that quantum mechanics was incomplete, but his instinct that something deep and important was going on with those correlations was absolutely right. Schrödinger was right to call entanglement the characteristic trait of quantum mechanics, but he probably couldn't have imagined that it would become the foundation of a theory of spacetime. Bell was right that the question could be settled experimentally, but it took decades for the experiments to catch up with his theorem. Feynman was right that quantum systems could only be properly simulated by quantum computers, but he didn't live to see anyone build one. And Hawking was right that black holes radiate, and right that this creates a paradox, and wrong about information being destroyed, and brilliant enough to eventually admit it. That's how science works. It's a human enterprise, full of human drama, And the ideas that survive are the ones that keep explaining more, keep connecting more, keep opening up new questions that are even more interesting than the ones that came before. And entanglement has done that more than almost any other idea in the history of physics. It started as a philosophical puzzle, a thought experiment in a 1935 paper that most physicists ignored for 30 years. And it's become the central concept in quantum information science, a key to understanding black holes, a candidate for the fundamental fabric of spacetime, and the basis of technologies that are being built right now, today, in laboratories and companies around the world. So here you are. You've traveled from Max Planck's reluctant hypothesis in a Berlin lecture hall in 1900 all the way to the frontiers of 21st century physics, where researchers are trying to understand whether the space you're lying in right now, the distance between your pillow and the ceiling, the gap between the Earth and the nearest star, is itself a manifestation of quantum entanglement. That's quite a journey for a quiet night. And the beautiful thing is, the story isn't over. It's not even close to over. There are questions that haven't been answered yet, experiments that haven't been run, connections that haven't been made. Somewhere right now, a graduate student is staring at a whiteboard covered in equations, trying to figure out how entanglement entropy behaves in a cosmological spacetime that actually looks like ours, not the idealized anti-de Sitter space where we know how to do the calculations. Somewhere, an experimentalist is cooling a quantum processor to a fraction of a degree above absolute zero, trying to maintain coherence in a few more qubits for a few more microseconds. Somewhere, a theorist is lying awake, not unlike you, turning over the implications of ER equals EPR, wondering whether there's a version of the conjecture that could be tested, even indirectly, even in principle. The questions are still open, the mystery is still alive, and honestly, that's the best part. Because the universe doesn't owe us a tidy explanation. It doesn't have to make sense on our terms. But it keeps rewarding us for asking, keeps revealing structures more beautiful and more strange than anything we could have invented. And at the center of it all, at the center of the weirdness, the beauty, the frustration, the wonder, is this one extraordinary phenomenon. Two particles, separated by any distance you like, sharing a connection that can't be explained by any signal, any force, any hidden message passed between them. A correlation that just is fundamental, irreducible. The characteristic trait of quantum mechanics, as Schrödinger said. Maybe the characteristic trait of reality itself. Your eyes are heavy now, probably. Maybe they've been closed for a while. And that's exactly right. You don't need to hold on to all of this. The details will be there whenever you want to revisit them. The names, the dates, the experiments, the equations. What matters right now is the feeling. The sense that the universe is stranger and more deeply interconnected than it appears. That the space around you, the time passing as you drift toward sleep, the very fact that the world feels solid and local and classical, all of that might emerge from something deeper, something quantum, something entangled. So let that thought settle over you like a blanket. The universe is woven from connections, and you're part of it, entangled with the air in your room, with the photons that touched your eyes today, with the atoms that were forged in stars that exploded before the Earth existed, not in some vague, hand-wavy way, in the precise mathematical, experimentally verified way that quantum mechanics describes. You are correlated with the rest of the universe, and the rest of the universe is correlated with you. And those correlations, quiet, invisible, spooky, might be the most real thing there is. Sleep well. The universe will still be entangled in the morning.